So we've spent some time talking about what we call basic recursion, and I alluded to the fact that there exists another famous kind of recursion. That's what we're going to talk about now. And that kind of recursion is called tail recursion. Tail recursion is best discussed in the the context of basic recursion, because it's kind of a way to repair a problem with with basic recursion. And what is that problem? Well, if we go back to where we were before, look here. It seems as if, to me anyway, it seems that the winding phase is where a lot of the work kind of was, because really I just want to stress adding in a stack frame really does cost work. Okay, so there's actual work involved for the computer, for the processor, when we have to build another stack frame. Okay, so um, here it seems that once we've done all this work, it's kind of wasteful to actually proceed with this unwinding, isn't it? Because we've kind of visited this 2. This 2 came from here. We visited this 3. This 3 came from here. We visited this 4. This 4 came from here. So we would like maybe some way to short circuit this unwinding. Okay, we'd like to short circuit that unwinding. And the way we do that is through this process called tail recursion. Tail recursion. And what is tail recursion? Well, tail recursion is a way to short circuit the unwinding procedure, which is kind of great, isn't it? Because we've saved just under half the work. For many goes. I think you can probably see that if we wanted to compute 20 factorial, we would have 41 stages, so it would be 2 times 20 plus 1. So in the limit, it's kind of roughly half anyway. But really what I'm trying to just get used to here is the idea that really this is what we're doing. We're shaving off about half of our work, okay? And we don't necessitate this this kind of popping. Now, maybe it's best to discuss this in the context of in a more mathematical context first, then we'll kind of visit how this is implemented in the stack. Because notice here, if we want to short circuit the unwinding, we'd still have to pop all these stack frames anyway, so we wouldn't really kind of be helping anyone, would we? So really, tail recursion, its most powerful benefit is that compilers are really very well optimized to take advantage of it. And actually, the compiler won't even do this. The compiler will not build 4 stack frames. It will not build 3 new stack frames. What it will do is it will overwrite the first stack frame, and I'll just show you. Firstly how tail recursion works by writing a tail recursive implementation of n factorial. So this time we're going to talk about not f of n, but we're going to talk about f of n and another variable a. And why on earth would I want to do that? Well, if we want to short circuit the unwinding, the best way to do that perhaps is to maintain the result of the calculation at every step. And that's what this a is going to do. This a is going to maintain the current value of the factorial, or what we think it is so far, how far we've proceeded with our calculation. And what we're going to do this time is, well, we're going to say if n is less than 0, again, we're going to get a sentinel value, so we're going to get -1 if n is less than 0. But this time something slightly different happens. If n is equal to 1, we actually don't get n, we get a. But please try to understand that makes perfect sense because a is the current value of our factorial. It's where we are in our calculation. And once we've kind of whittled our way all the way down to 1, once we've whittled our way all the way down to 1, the only thing left to return is this. And essentially what we've done is we've short-circuited the unwinding because the unwinding phase becomes really, really quite simple. There's no work to actually be done in the unwinding phase. And really that's something I want to kind of say here as well. The way it does this is by arranging it so that we arrange for the unwinding phase to involve no calculation. No calculation. All of that is kind of going to be fed into our winding phase, which we're already kind of forced to do anyway. So okay, so -1 if n is less than 1, a if n is equal to 1 because this is our current value, and when n is 1, we're done the calculation. And finally, if n is greater than 1, what we actually do is we get f of n minus 1, and let's give ourselves just a small amount more space, f of n minus 1 and n times a. Okay, so what this does is this update, I want to just kind of talk us through what happens, is we update our current stored value, and here we signify that we are closer to the end of the calculation. And now you might be wondering, well, essentially we've done this. We've stated a tail recursive version of the factorial function, but you might be wondering, Sean, you've told me the factorial is a function of n. What is this a? What should I start with? Well, a little thought should tell you that the initial value should be 1. So f of n and 1 is going to compute n factorial for us. This is going to compute n factorial. Why? Because our initial guess is 1. That's an empty product. Our starting point is the empty product. Then we multiply in n. Then we're multiplying n by -1. We keep going all the way till we get down by 1. So the starting point is the empty product. This is the empty product. Okay. So let's kind of do an example. Well, the example we've been doing is 4 factorial. So 4 factorial, and we're going to compute that as f of 4, 1. Well, let's see what happens. So we have f of 4, 1. Well, 4 is greater than 1, right? So what we're going to actually get, is f of, and n should be reduced by 1, so we're going to get 3. But here, what we're going to have is 4 times 1. So we're going to have 4 times 1, which is going to be 4. And I'm going to signify that I got it by multiplying these two together by underlining them, okay? And very good, we've moved on with our calculation. Well, what's going to happen now is we want f of 3 and 4, and how are we going to do that? Well, f of 3 and 4, again, 3 is bigger than 1, so what we do is we decrease n by 1, so we're going to have f of 2, and then we multiply these together. We take n times a, and 3 times 4 is 12, and just to signify where I got that from, I'm going to say 12, and that's the product of these two here. Very good, so we're kind of getting closer. So we have f of 2 and 12. Well, what's this? F of 2 and 12. Again, we reduce we reduce n by 1, so 2 minus 1 is 1. And here we're going to put the product of n and a, so 2 times 12 is 24. Hopefully a number that we recognize by now. And essentially we're done because f of 1 and 24, well, that's just equal to 1. This is the base case. This is the base case. Right, so we've whittled it all the way down. This is the base case. And please excuse me, I've just realized I've been a bit silly because we should report A. We should report A. We should report A. So this is going to be 24, and we should report 24. But please notice that we're done, because here, look, let's pull ourselves back. Let's give ourselves a small amount of extra space, and here we've completed the winding phase. So this is winding. This is the winding phase. Let's write it more neatly. Winding. Well, look what's happened here. Here we've got 24, but there's no work to be done. Look what happens here. There's no work to be done. So we're going to write f of 2 and 12. Well, that f of 2 and 12 is just f of 1 and 24, but f of 1 and 24 it's 24, right? We just worked that out, right? And then we say, okay, that's fine. Well, we just go back one step and we say, well, okay, then what's f of 3 and 4? Well, f of 3 and 4 is f of 2 and 12, but we've just worked out f of 2 and 12, so that's going to be equal to, well, surprise, surprise, 24. Notice as we unwind, there's no work to be done. There's no work to be done. And finally, we're going to say f of 4 and 1. Well, what on earth is that? Well, look here, f of 3 and 4. But we've just worked out f of 3 and 4, and the result is 24. And this is our answer. We have that 4 factorial is equal to 24. And I think it kind of pays to just draw a stack diagram of this. So we're going to quickly just draw a stack diagram just to kind of see what happens. So let's just start with the first phase of our computation. What's the first phase of our computation? We're going to draw a stack frame like this. So we're not going to spend any time on this. We're just going to kind of rush through. Well, at the start, we have n equals 3, and we also have a equals 1. Okay, and we want to leave a bit of space for our return value. We kind of have our no man's land here, and we're going to leave a bit more space for our input to the next recursive call. Okay, so this is our no man's land here, the area that's kind of requisitioned for this particular stack frame to do any internal computations. Okay, very good. Well, now let's just keep going. So we're going to push another stack frame on top, and we do that by saying, okay, well, we're going to pass n equals 2, and a is equal to 3 times 1, so a is equal to 3 here. We're going to have n equals 2. We're going to push a equals 3 here, and when we do that, we're just going to tack on another stack frame. We'll make some room for the return value. We have our no man's land here. No one's allowed here. And finally, at the bottom, we say, well, what we're doing is we're going to the next call. So the input here, well, let's just kind of just be clear about this. We don't know the return value yet, so we don't know the return value here, and we don't know the return value yet. But what we can do is we can reduce by 1. Please excuse me, this is 3 factorial, not 4 factorial, so I should have started with 4. So this is 4, and a is equal to 1, and that would have given me excuse me, I've just messed up here a little bit, but nothing that's unrecoverable. What we've done here is we've got n is equal to 4, a is equal to 1, then we reduce, so we get n equals 3, and a is equal to 4. And we have n is equal to 4, a is equal to 1, because that's the beginning stack frame. Then we have n is equal to 3, a is equal to 4. And finally, we're going to have n is equal to 2, because we're reducing that n. And we're going to have a is equal to 3 times 4, which is 12. So this is our second stage of computation. Next, we kind of say, okay, let's kind of go to the next one. This is our third stage of computation. We're going to tack onto our stack frame. We're going to tack on another stack frame onto the stack. So we're just going to push this onto the stack. Let's get the output here, the return value here, and well, n is 2, it's not 1, so we don't know what it is. We don't know what the return value is, so that means we have to make a recursive call. We have to make a recursive call and spawn another stack frame, and that stack frame is going to see n is equal to 1 and a is equal to 24, right? And now, this is the end of the winding phase, I think you can see here, because what's going to happen is I'm going to draw in another stack frame. I'm going to draw in another stack frame. Oops, please excuse me. That's just another stack frame like this. And well, we do know the answer this time. We absolutely do know the answer. And this is kind of this is our no man's land. And we do know our answer. This time we have 24 because n equals 1 was 24. So now we're just going to unwind. So we're done with our winding. We've done winding. Now it's time to unwind. So how are we going to unwind? Well, the same thing we did before, but the difference here is there's actually no work to be done. There's actually absolutely no work to be done at all, because 24 is just going to get passed up to the next stack frame. So here, we pop, remember we pop the bottom frame, and here, look, there's no calculation to be done. There's no calculation to be done whatsoever. There's no calculation to be done whatsoever. So what's going to go here? Well, 24, right? 24 is what got returned. So again, this is going to give us this is the fifth stack frame, the fifth view of the stack frame, the fifth stage of our computation, or the fifth view of the stack, and containing 3 stack frames. So we have 6 here, and again we pop from the bottom of the stack frame. So the bottom of the stack, excuse me again, or well, the top of the stack, we pop from the top of the stack, and we say, okay, well, this is not unknown anymore. It's not unknown anymore because we know that it's 24. And what we've done here is we've returned 24 directly here. We've returned 24 directly here. And finally, we're going to get to the situation where we're done, because at the seventh point, we're going to just grab this. Oops, excuse me. Going to grab this, and we're going to pop from the stack, and we're just in our initial stack frame here. And again, what happens is this return value just gets passed up the chain, and it becomes the return value here. So we're going to get a 24. We're going to get a 24 here, and we've concluded at the end of our unwinding, which notice involved no work. So if we go back to our one before, here, what we have here is work to compute that. We have work to compute that 6. We have work to compute that 24. But please understand that here, no work is involved in the unwinding phase. So there's no work here, and there's no work here when we're unwinding. And so what we've done is we've worked out that f of 4 is of course equal to 24. This was our result. Now, I think you can see why this is wasteful, and I alluded to what the way to get around this was before. What we do is, instead of building, we instead of pushing onto the stack, we kind of overwrite the stack. So essentially, pushing is wasteful when unwinding involves no work. Instead, let's overwrite. We're going to overwrite the stack. We're going to overwrite the stack. What do I mean by that? So again, we want f of 4, so 4 factorial. Well, f of 4 and 1, right? So f of 4 and 1. Well, let's start with the first stage of our calculation. I think we're going to need a bit more space than this, so we're going to just get ourselves a bit more space. So what we're after is f of 4 and 1, and that's going to equal question mark, because we're going to figure that out. We're going to have a 1 here, and we're going to have a we have a 1 here, and here, this is the top of the stack, this is the bottom of the stack, and we can kind of use as much space as we want vertically, because you know we're not actually going to be pushing onto the stack. We're going to be overwriting. So once we've done that, we say, okay, well, here we started off with n is equal to 4 and a is equal to 1. Well, we don't know the answer. So what we do is our outgoing parameters are going to be n equals 3 and a is equal to 4 times 1, which is 4. But instead of spawning a new stack frame, why don't we just overwrite? Why don't we just overwrite the input values and do the calculation again? So we're going to have n is equal to 3, we have a is equal to 4. We keep that question mark because we don't know, and then again we just put in our outputs. We have n equals 2 because 3 minus 1 is 2, and we have a becomes 3 times 4, which is 12, okay? And this is the second stage here. Very good, so what next? Well, if we kind of plot this here, if we just plonk this here, what's going to happen is we get overwriting again. We overwrite our stack. We overwrite. And I just want to make that explicit here. Here, we're not pushing, we're overwriting. We're overwriting. And here we're not pushing, we're overwriting. And we have n equals 2, so we're overwriting n, and we're overwriting a in our inputs as 12. And again, n is not 1 yet, so we can't stop. So what we have to do is reduce n by 1, so 2 minus 1 is 1, and a becomes the product of the input, so 2 times 12, excuse me, is 24. And finally, we do have n equals 1. In our last view of the stack, which consists of one stack frame. Please understand there may be many more stack frames above, but we're not interested. We're interested in the beginning point of our calculation. But here we're going to write n equals 1 and a equals 12. But here we're done. We're done because we know that that's 24. Okay, so here what we've done, because again, clearly I can't copy because that's n equals 1 and that's a is 24. So we're just copying that 24 in there. And really, I hope you kind of understand. Again, all we've done is we've overwritten. We're overwriting. We're overwriting again. But here, notice, this is the winding phase. But The stack only has one stack frame on it that we're interested in. No unwinding is necessary. So there's no unwinding. So we've saved two things. We've saved the work it takes to allocate a new stack frame 4 times, and we've completely saved 3 steps of calculation. We've saved three pops. So we have saved 3 pushes onto the stack, and this of course is our we've done this by overwriting. Maybe I should do that in purple to be consistent. By overwriting, and we've saved 3 pops. We've saved 3 pops, and this is because there is no unwinding. And there's no unwinding. Why? Because we didn't push anything onto the stack. And now you can see, essentially this here, you might ask kind of like, well, what good is this? I've just said what happens if we do decide to overwrite instead of push. Well, computers are, they're very funny about the way they do things. They have to do them this way because, that's how they were built. They're insistent on doing things in this way and this way only. However, compiler writers are very clever. They write compilers to detect tail recursive functions. Okay, so good compilers can do 2 things. One, they can detect tail recursive functions. And 2, what they do once they've done that is implement this optimization. So what they do is the machine code will look more like this than it will look like this. And you'll have shaved off 3 pushes and 3 pops, okay? Saving you indeed a really good amount of work. And also, I should say before we go that I don't want you left with the impression that for the basic recursive solution that we could have just done this, because I hope you understand that the state is not stored externally. So if I overwrote this, I'd have no way of knowing that I had a 3 beforehand because I hadn't done my computations. I'd have no way of knowing I had a 4 beforehand. I'd have no way of knowing I had a 2 beforehand or a 1. Once I get down to a 1, essentially that's kind of it. Here I have no more information. I have absolutely no more information, right? The information comes from the fact that to step here to here, I have to multiply, but the multiplications are done in the winding phase. That's the key. The key is I can do something like this that removes the winding phase because there's no work to be done in the winding phase. Look, the winding phase involves passing this 24 up, but the 24 is exactly where it needs to be, right? So no work needs to be done. So I really want you to understand that this optimization is only possible because there's no work to be done in the unwinding phase. That is why we can do it this way.